Hi everybody, welcome back to the FPV Drone Racing course on HackadayU. My name is Ayan and today we are going to be talking about flight controllers in class 4. So until now we have discussed about what are drones, what are the physics involved with drone, the propeller selection guide, then we talk about different frames that are available, different types of frame in terms of material, number of propulsion system. We also talked about the motors and electronic speed controllers and batteries. And today we're going to be talking about how the flight controller helps a drone take a stable flight, the level flight, and how it compensate for the external forces and internal defects. And what is a digital signal processing? Why you need that? What is a control system? Why you need that? PID and all that stuff. So in the class 1, you might remember that I told that drone needs to be having motion in three different axes, that is the pitch axis, the roll axis, and the yaw axis. These are the degree of freedom. And if the drone pilot or the drone operator wants the drone to go in the roll left axis, then if this command is given from the remote or the transmitter, the flight controller process it, and it rotates the right motors up at higher RPM and the left motors at lower RPM. So the overall thrust coming from the right is more, and the drone will go in this direction. So how much RPM to rotate at which motor, that is calculated by flight controller, and how that calculation happen, how that computation happens, we'll talk about today's class. Also, we'll talk about why you just cannot just plug in four motors together and just give them power and without any flight controller try to fly it off. And trust me, that's not possible. So we'll talk about all this in today's class. So without further ado, let's start. Alright, so we are on the computer screen and let's begin with today's class. That is class 4th on flight controllers. So the agenda for today's class is this. We will talking about flight controllers and digital signal processing. Why do we actually need a flight controller? Why can't we just plug in, connect four motors and four propellers and just let the drone fly? Why do we need computation? And similarly, why do we need sensors in our drone? Accelerometer is there, gyroscope is there, and we'll also be touching about how many sensors are there, but why do we need that? We'll also talk about what is an inertial measurement unit and degree of freedom, and this is quite an interesting topic. Then we'll talk about the basics of digital signal processing and what kind of signal processing do we actually need when we are making drones. And under that, we'll talk about sensor fusion, data filtering, what is read frequency, what are filters. Then lastly, we'll talk about what is control system and why do we need control system in our drone. And we'll also talk about the proportional integral derivative, that is the PID control system, the maths behind this, and we'll have a small discussion on PID tuning. And if you are among few who have already made a drone, then you'll know that this thing is really messy and a lot of people don't really get it. And in the end, we'll talk about the connection of the flight controller. So let's begin. Alright, so in the first class, I talked about the different axes of motion on which a drone has a freedom. So these are basically called degree of freedom. And if you talk about drone, a drone can do the roll motion, the drone can do a pitch motion, and a drone can do a yaw motion. And of course, you can take your drone up and down if you increase the value of throttle. So these are the degree of freedom that is available in the drone. And I also talked about a concept called motor mixing, which I just explained in the introduction, that a flight controller, it changes the RPM of motors, mostly two at a time, to give you a particular a degree of freedom authority. So of course, if you want to go roll left, your right motor will spin up, your left motor will spin down, and overall thrust coming from right will be more than the thrust coming from left, and your drone will go in that direction. So that is exactly how a drone works. But the topic of today's class is how this is happening and how much RPM a motor should be revolving at, how flight controller calculates that, and all kind of things. So we'll touch upon that. So again, this is the same thing which I just said, that if you want to go roll left, your right motor will spin up, your left motor will spill down. If you want to go roll right, opposite, the left set of motor will speed up. The right set of motor will speed down, and the overall thrust coming from one direction will be more than the other, and you will get the desired motion. Same goes for yaw, but in the case of yaw, there is the diagonal motor which comes into the picture, two at a time, the diagonal motor, and the pitch you'll have the back and the front motors. So you might remember this slide from the first class, and this slide says that UAV multi-rotors are aerodynamically unstable, and I've mentioned in the first class they don't have the design which allows them to stay in air stably. They don't have airfoil, so they are basically unstable, and to become stable, to hover at one place without much changing their position, they require computer, and computer requires sensors. So the first step is to sense where you are, and the second step is to sense where you are going, and if that matches what user wants, if not, then compensate it by changing the RPM of motor. So that is exactly how a drone work. And to obtain that, the drone flight controller, it has a program, it has a firmware running, and the responsibility of that firmware is to do all these mathematical algorithms and computation, and instruct each motor at what RPM to spin at what particular instance. So let's see how that works. So this is the brain of the drone. This is the main component which helps you do this, which we just talked about. So this is nothing but a flight controller, and the picture I'm showing is one of the famous flight controller. But there are like thousands of flight controller in the market. Each one have different PCB layout. Each one have different kinds of sensors. Maybe same sensors from different company. Maybe same sensors but different configuration, and we'll talk about that as well. And this is a most common FPV flight controller, which has accelerometer and gyroscope, and has one CPU. As you can see, this ARM STM32F4. This is the main chipset which do all the computation, and this is the chip which has accelerometer and gyro. So what exactly is happening here? So on the right, you can see how the flight controller talks to the ESC. So basically, flight controller and ESC has communication going on over a signal line, which is also known as ESC signal. And the flight controller also gets signal from the receiver. So basically, what is happening in this case is this transmitter, or let's assume there is a pilot using this transmitter, a drone operator. The drone operator is using this transmitter to send signal to the receiver, and we know what kind of signal it will send. It will send what value of roll I need, what value of pitch I need, and what value of yaw I need, and what is a throttle, and these kinds of things it can send. So all these values will be passed to the receiver, and receiver will pass it to the flight controller. So flight controller knows what the user wants. Flight controller knows that the drone operator wants me to, let's say, wants me to give a roll of 3 degree to the right, or wants me to give a yaw of 7 degree to the left. So these kinds of thing the receiver will pass to the flight controller. Now it is the duty of flight controller to do the function that the drone operator wants the flight controller to execute, and how it's happening. So it will do all the maths. It has the firmware which is responsible for doing all the maths. So after doing all the maths, flight controller will send signal to each and every ESC, and it will tell them to what RPM you should be rotating at that particular instant. So exactly as I mentioned in this flow chart, the drone operator is sending the value of a roll, pitch, yaw, and throttle to the receiver. Receiver pass that to the flight controller. Flight controller computate the current RPM of each motor and pass it to the ESC. And as the name suggests, electronic speed controller, they will ultimately control the speed of the motors. So receiver and flight controller communicates with one another over a protocol that we have already discussed in class 2. Flight controller and ESC talks to one another over a particular protocol that we discussed in class 3. So ultimately everything is sorted. They are able to communicate with one another, and you get the desired motion of the drone. And again, every ESC needs some power, so you can also see the battery in the picture as well. So this is the overall what you can say is architecture diagram, or the functioning of flight controller in this one slide. Alright, so coming back to the flight controller, which is the brain of the drone, I just want you to look thoroughly to this picture. So this is a flight controller. It's really small, but it packed a lot of things. So over here you can see this is the main CPU, which is responsible for holding the firmware. The firmware holds all the algorithms and all the mathematics equation which it needs to computate. So this is the main CPU, and this CPUs can be different on different flight controller. For example, this one has STM32F4 based. You can also get F1 based, F3 based, or you can get an entirely different chip if you are doing more than let's say FPV flying. For example, if you are doing autonomous drones, then it has more powerful CPUs and more powerful sensors. So This is the main CPU, which is holding the firmware. Then over here, this is the chip which contains the sensor. It's known as IMU, or inertial measurement unit. I'll talk about that in a bit. And these two are basically the main part of the flight controller. But these days, flight controllers are getting a lot of advancement, and because of that, they are getting more and more elite day by day. So as you can see, this is another big chip here. So this is nothing but an OSD, which sits between the camera and video transmitter, and it overlays a screen of information like your current battery or your current ampere usage. But we'll talk about that in maybe some future classes when we talk about FPV. So you can see that over here, these are the pads where you solder the ESC wires, where your flight controller and ESC will communicate through. So these are the solder pads where you can solder the signal wire of your ESC. And over here you can see ground, 5 volt, RX and TX. So these are the UARTs, and here you can solder the receiver. So receiver, if your receiver works on S bus, it uses a UART for the communication. UART basically is a communication protocol, serial protocol, universal asynchronous receiver transmitter, and over here you plug the receiver. So as I showed you, you plug the receiver, you plug the ESC, you plug the battery, and the flight controller is good to go. So this is how a flight controller looks like, a typical FPV drone flight controller. And this, again, I mentioned this has nothing but a CPU and something called inertial measurement unit. So what is an inertial measurement unit? So I'm sure that all of you have heard that your phone has some kind of sensor. I'm talking about mobile devices, your mobile phones or tablets. So let's take an example that when you rotate the phone, your screen also rotates. Let's say you're watching a video in a portrait mode, suddenly you decide to watch it in the landscape mode. You rotate your phone and your video gets rotated. So it's because it has sensors, and the sensors detect the change of the phone attitude, and accordingly it sends signal to the program playing video that I want to play the video in landscape mode. So the sensors responsible for that is called accelerometer. And similarly, your phone has more than one sensor. It has accelerometer, it has gyroscope, maybe it also has the magnetometer. Nowadays, it also has a barometer, so it can tell you how high you are from sea level, or how many floors you have climbed in a day. So a common misconception is that there will be different sensors in the phone, but actually all the sensors comes inside a same package. And what I mean by same package is that this single chip on the right, this small chip, these have all the sensors, and this one chip has accelerometer and gyroscope in this case. But this kind of similar chip can also has a magnetometer or a barometer. So the single package containing all the sensors, it's called inertial measurement unit, or IMU for short. And an IMU can be made by different companies. So it's not necessary that only one company made IMU. Maybe you can get an IMU from ST Microelectronics. Maybe you get from Texas Instruments. So I believe this one is made by ST Microelectronics. I'm not sure, but I'm pretty sure that the chip name is MPU 6000. So MPU stands for Motion Processing Unit 6000, but that is none of our concern. We only concern about what it has. So this one has accelerometer and gyroscope. So on a flight controller, on a typical flight controller which we use for FPV flying, you'll get accelerometer and gyroscope. And to be more precise, 3-axis accelerometer and 3-axis gyroscope. Now the question is, why do we need 3-axis accelerometer and 3-axis gyroscope? So it's simple, because the degree of freedom for drone is 3, and you need one for each axis. That is one for roll, one for pitch, and one for yaw. Similarly, gyroscope 3-axis, one for yaw, one for pitch, and one for roll. And this chip IMU is sending data to your main CPU over some protocols. So these protocols are generally I2C, Inter-Integrated Circuit, or SPI, Serial Peripheral Interface. So these are the common chip-to-chip communication protocols, or digital protocols, serial protocols that IMU used to communicate with the main CPU. And the data rate at which they can send data is let's say 8 kilohertz, 16 kilohertz, 32 kilohertz. So that means it's sending 32 into 10 raised to power 3, I guess 32,000 values per second. So that is how much data it's sending at 1 second, 32,000 different values of yaw, pitch and roll in 1 second. So you can imagine a lot of data and a lot of computation is required. So this is the entire inertial measurement unit, and that's how the communication is happening. Since on the flight controller the CPU and IMUs are on the same PCB, that's why they are integrated in a same PCB, and you don't see any wiring going from this to this. But again, internally they are connected using PCB tracks, and they communicate over I2C and SPI. SPI is faster. I2C is relatively slower. So on I2C you cannot get let's say 32 kilohertz of speed. So if you want to go for a flight controller which has IMU capable of sending 32 kilohertz data, then you will need to have an IMU which supports SPI. So MPU 6050, which is a very common IMU that doesn't support SPI, that works on I2C. So you are restricted to 8 kilohertz data rate. But if you want 32 kilohertz, you will need to go for an IMU like MPU 6000, I guess, which can do 32 kilohertz. The overall thing happening here is more the data, more information CPU has to process, which might sound counterintuitive, but actually more data is useful. So if you are sending more data, then you know more precisely where your drone is at one particular instance. So that is why you need IMU with higher data rates. Okay, so let's talk about degree of freedom. So as I mentioned, drone has a roll, pitch and yaw degree of freedom, and for each axis we need an accelerometer or at least a gyroscope. So if we are buying a flight controller, we can consult that how much degree of freedom the IMU inside the flight controller supports. So a typical IMU, it's a 6 degree of freedom IMU. And what I mean by 6 degree of freedom, that it has 3 axis accelerometer and 3 axis gyroscope. So 3 plus 3 combines become 6. So that is why it's called 6 degree of freedom, or 6 DOF in short. Now there are some more advanced IMUs and more advanced flight controllers containing this IMU, like 9 degree of freedom. So a 9 degree of freedom IMU will have everything that a 6 degree of freedom has. That is 3 axis accelerometer and 3 axis gyroscope. Apart from that, it will also have a 3 axis magnetometer. So that becomes a 9 degree of freedom, and we'll talk about what each of these do. Then we'll have 10 degree of freedom. So it will have everything a 9 DOF IMU has, but it also has a barometer. And what it is happening here is that with the help of accelerometer sensor, you can measure acceleration. That is acceleration in one axis, for roll, there would be different acceleration for pitch and for yaw. Similarly, gyroscope helps you to find the angular velocity or a particular axis. What is the angular velocity in one particular direction? Let's say pitch. So with the help of gyroscope, you can measure that. And with the help of magnetometer, you can find the magnetic orientation for your drone. So we all know that Earth has the magnetic field of its own, and with the help of compass we can find where is the north. That is the same function the magnetometer does. It tells you where is the north, and it will tell you the magnetic orientation of your drone. And with the help of the barometer, you can calculate the altitude. So nowadays fitness smartwatches and even smartphone, it comes with an altimeter or a barometer. It's nothing but a barometer which is capable of sensing the change in air pressure as you move to a height, and with the help of that it can tell you your current altitude from sea level, from ground level. So that is a function of a barometer. So the question is how these sensors are made so small that they can fit in one single chip, as you can see on the left. So the answer lies in piezoelectricity. So piezoelectricity is a concept where you can make electricity from some kind of motion and vice versa. So piezoelectric crystals are basically the substance used for making these kinds of sensors, and they are relatively very small in microns. And these piezoelectric crystal, when you make motion in one axis, they generate some electricity, some electric current, and inside the chip you can have some amplifiers, and you can find how much current is generated, and you can find the motion in one particular axis. So this concept is known as piezoelectricity, and the substance that shows piezoelectricity are called piezoelectric materials. So that is how these IMUs are integrated in smaller chips, and that's how they are manufactured. Alright, so I mentioned that with the help of accelerometer you can calculate the acceleration in one direction, and with the help of gyroscope you can calculate the angular velocity in one direction. And if your drone also has a magnetometer, which is not very much common in case of FPV drones, then you can also calculate the magnetic orientation. But as I mentioned that the IMU is communicating with the CPU over I2C and SPI, and with a very high speed data transfer. The problem that is often seen in these kinds of communication is noise in the system, and this noise sources can be anything. It can be the noise coming from the vibration of your drone or your motors. Maybe your motor is not correctly mounted and it's vibrating when it's rotating. So these kinds of problem are also very common when we are talking about communication between the IMU and the CPU. But again, as I mentioned that you can definitely measure the linear acceleration and angular velocity using accelerometer and gyroscope. But at the end of the day, we are more concerned about the angle of the drone and not the acceleration and not the angular velocity. We need to calculate what is my roll angle, what is my pitch angle, and what is my yaw angle, because at the end of the day, this is the data which you are more considerate about, and this is the data which you need more, and you need to compute it on that particular angle. You don't need the linear acceleration or angular velocity. So how can we solve this problem? And as I mentioned that noise in the signal can be from mechanical vibration, it can be electrical noise, and in the motor chapter I mentioned that the new ESC has something called regenerative braking, and when the motor is brake, some electricity, some voltage is sent back to the signal. It's called back EMF. So these kinds of things generate noise in the system, and it can very easily give the false information to the CPU that this is not the correct data coming from IMU, but some distorted data. There is some other problems which are problems related to these sensors, and these are universal in nature, and you cannot just ignore that. For example, the value of a gyroscope drifts over time, and that with drifting I mean that the value of gyroscope keep on changing over time, and you cannot rely on gyroscope value in very longer duration for that reason. And the accelerometer values, they are very noisy, and even if you do very small motion, very small motion, you will get a change in the accelerometer value, and that is why it's not very reliable for short term duration. So with these problems in system, you cannot just use accelerometer and gyroscope straight away to make a reliable drone, and you need something which can counter these problems. And what is the solution? The solution lies in digital signal processing. And now that you know that we have all these problems, we also have the solutions, and the solution lies in DSP or digital signal processing. So what exactly is DSP? It's like filtering of signals. So what we need to do is we need to filter the main signal out from the noise. We need to filter out the noise. We don't want noise in that in our system, because noise gives false information. Because of noise, your CPU will get false information, and it will do false computation, and you will not get the desired results what you want to do with the system, or in our case the drone. So we need to filter out the noise, and we can do that with using DSP, and we'll talk about how. The second thing which I mentioned, that accelerometer gives you the linear acceleration and gyroscope gives you the angular velocity. But how you can use these two different values to find the angle of one particular axis? The answer lies in sensor fusion. So we can combine multiple sensor value and we can calculate what we want and not exactly what they give. So we'll talk about these two powerful concepts, and trust me, these are the very powerful concept, especially sensor fusion, and it's being used everywhere in today's world, in self-driving cars, in your printers, in everywhere you can see these kinds of concepts are being used. So let's talk about how they are being used in the drone. So first of all, let's talk about filtering, and what we need to filter here. We need to filter the noise from the system. We need to filter the noise which is coming with the actual value of accelerometer and gyroscope. So filtering can be as simple as mounting your IMU on a vibration dampening base, or it can be as complex as designing a multiple order filter in the firmware. Example, notch filter. So you need to ultimately reduce the vibrations coming into your system, because as I mentioned that even the small motion can generate some values in the system which you don't want. So what you can do is you can either mount your IMU, or in this case flight controller, because IMU is on your flight controller. So what you can do is you can mount your flight controller on a vibration dampening system, so it doesn't affects if there are vibration coming in the system. And what else you can do is, that is not the solution. Maybe your drone frame is really small, you cannot add a vibration dampening. What you can do is you can design a filter in your firmware, and you can program the filter. And example is a notch filter. So what's a notch filter do? Notch filter will identify the noise source, will identify the noise signal, and it will filter it out. Similarly, you can use a low pass filter that will filter the high frequencies. And when I talk about noise, these are generally high frequencies in the system. So you can design a low pass filter that will pass the low signal, low frequency signal, and it will block the high frequency signal. So one such good example is I can show with the overhead camera is. Here you can see in my drone I'm using this vibration dampening balls which we are using in our drone. So this ensure that there is no mechanical noise in the system. And similarly you can add that in the drone itself. So this is a bigger frame which allows you to add these kinds of vibration absorbers, and this ensures that the mechanical noise coming from the vibrations in the drone. So moving part of the drones are generally motors, and they create vibrations. So this will absorb the vibration, and your flight controller, which is having the IMU, will be mounted on the top of this plate. So overall, it's a really sweet hack to do, and a lot of people do that. It will give you a good flight. Tuning of the drone will be much easier because you are countering the vibration coming into the system. But again, it's not possible everywhere. It's something which requires space, and it's not possible in smaller drones. So what you can do is you can implement a higher order filter, as I have seen here. So this is again a complicated thing, but we are lucky enough that the drone firmwares are open source and we don't need to program everything. So we'll talk about that in later slides. But for now you can understand that we can filter the noise in the system using vibration dampeners or designing a filters in the firmware. So we solved the first problem of noise using filters or vibration dampeners. But what about the second problem? The second problem is relatively more complicated, where the sensors which are available to us on our drone IMUs, they do not directly provide the degrees of any axis, like what is the degree of your pitch currently, how much your drone is tilted in this particular angle. But it provides acceleration and angular velocity, but that is no use of us directly. So what we're going to do, we're going to use a concept called sensor fusion. And as I already mentioned, sensor fusion is a very, very powerful concept used in a lot of different industries like automation and automotive. In the automotive, it's really useful in self-driving cars, where you have a lot of cameras in your cars and you also have LiDAR. So you have different sensors and you combine all those, you fuse all those, and you come up with one value or one useful set of data that you can use for your advantage. So similarly, we will be fusing the accelerometer value and the gyro value together to get something of use. We may not get the angle directly, but we will try to estimate it. So let's see how that works. So let's see how we can use accelerometer to our advantage. So no matter how your drone is in with respect to the ground, no matter what is the pitch angle, roll angle, or yaw angle, the acceleration due to gravity will always face downwards, because the gravity pulls the object downwards. So we always know that in which direction the gravity is, that is the down. And if your drone is making some changes in this, let's say, pitch angle, so you see this is forming a right triangle, and with the help of a trigonometry, let's say tan theta, we know this distance and this distance, and we can calculate this angle. So this is a very powerful concept, and we can use the accelerometer to our advantage, and we can calculate this angle. But of course it is not much useful, because as I mentioned that the value of this data coming from the accelerometer, it's very noisy, and even very, very small change can give a huge deviation in the value. So it's not very helpful in shorter term. Maybe over longer term, let's say when your drone is flying for 5 minutes, it's maybe useful, but not for the shorter term, because it's very noisy to get value from accelerometer. And if you want to verify, you can just take an Arduino and use any accelerometer like ADXL335, and you can see even very small change will give you a very huge deviation in the data. So accelerometer values are no good in shorter terms. But how we can estimate using the gyroscope. So gyroscope, what it counts angular velocity. So how we can use that for our advantage? So let's say the angular velocity of this particular drone in pitch axis, it's 2 degree per second. Let's estimate that. So let's say we are moving our drone in pitch axis at 2 degree per second. So at the time of takeoff, the pitch angle is 0 degree. That is perfectly level with the horizon to the ground, and it's changing at the rate of 2 degree per second. So we know that after 10 seconds it will be 10 degrees per second or 20 degrees per second, excuse me. So what we have done is we have used the rate of change of one axis and we have integrated it over a time period. So this technique, it's called dead reckoning, that is integrating a value, a rate over the time. And this is very helpful if you want to calculate the rate of change of a particular set of time. But again, the problem here is value is not the only thing that is integrating over time. So these values also have some sort of noise, and this noise will also get integrated over the time, and over the time, let's say in 2 or 3 minutes, it will get almost unusable values because the noise will become too big after integrating in each cycle. So that is why I said in couple of previous slides that gyroscope values, it drifts over time because the noise is getting integrating over time, and it becomes very unusable to use only the gyroscope value over the bigger period of time. So that's what I mentioned, that noise is also get integrated. So the problem with accelerometer is the value, it's not usable for shorter duration. The problem with gyroscope is the value is not reliable in longer duration. So how we can use these two techniques, because these two techniques definitely giving us some useful data, but how we can use these two techniques to get something usable out of it, something which we can actually use for our advantage. And we can actually do that. So we can do that something with something using called complementary filter. And complementary filter is a very easy to implement, a very powerful concept. And what is happening here? So as I mentioned, that accelerometer not reliable in short term, gyroscope not reliable in longer term. So how we can take best of both worlds? So we can use something called complementary filter, where we pass the value of accelerometer from a low pass filter, and we pass the gyroscope value, integrated gyroscopic value from a high pass filter, and together we get a complementary filter, because the low pass filter is complementary of the high pass filter. That is, if your low pass filter is g of s, your high pass filter will be 1 minus g of s, and ultimately you will get the full value, that is the one value. So this is a very powerful concept and very easy to implement. Complementary filters are really smooth to implement. Even if you have some different application, let's say you want to build a self-stabilized robot which can be stabilized in 2 wheels, you can use something called complementary filter, where you can use a MPU 6050 IMU, which is very cheaply available. You can use it with the Arduino. You can put some motors, and you can pass the value of accelerometer from low pass filter, value of gyro from high pass filter, and over the actual value which you will get, that is the one value that will be the usable value which you can actually rely on. So this will give you the usable value, and it will tell you what is the current attitude of your system. In our case, it will tell us what is the attitude of the drone in X, Y, and Z, or the yaw, pitch, and roll axis. So again, this is called sensor fusion, and we literally fuse these two values. We take accelerometer value, we take integrated gyro value, and we fuse this together to use one value for our advantage. We use the best of both worlds. That is the short-term benefits of accelerometer and long-term benefits of gyroscope. And you can see this excitement, because when you actually implement this, it's a very powerful concept and very easy. So even for Arduino, like microcontrollers, if you have complementary filters, you can implement with some libraries. There are some open source library which help you implement complementary filter, and if you are into that, I would highly recommend you to do that and see for yourself. So again, this is called sensor fusion, and at the end you get something useful value. You get a degree, an estimated degree of one particular axis, which you can definitely use for your advantage. So that was called sensor fusion. Alright, so that was a complementary filter, but do you really see some disadvantage going on over here, and which is quite significant, especially if you see that you are getting data at speed of 32 kilohertz, that is 32,000 values per second. So one thing which I can definitely see right away is complementary filter is using old values and integrating it over time. So over time, a lot of different values will be integrated together, and you need to store these old values, and it will become really costly on memory and computation power, and to integrate it and do all kind of things. So that is one drawback I see, and of course we are getting the angle, but do we really need the absolute value of the angle, or we can do some kind of estimation? So to overcome these kinds of disadvantage, we have something called Kalman filter, and this is a really advanced filter. It's so advanced that I don't want to even show you the equation so you won't get intimidated, because the first time I saw the maths behind Kalman filter, I was really intimidated, and it took me a lot of time and a lot of efforts to actually understand it, and to actually implement one for myself. And the reason I don't want to go into that much detail, because not everyone would be implementing it themselves. So you do not have to invent the wheel. There are already people who are good programmers, who are good scientists in this domain of digital signal processing, who have done that, and they are provided some libraries for us. So we can definitely use those libraries and implement Kalman filter. But because the drones are getting more and more advanced, and the IMUs are getting more and more faster, even in drone racing, you are flying at speed of 150 miles per hour. So you need to have relatively faster filters. You need to do sensor fusion really fast, and that is why Kalman filter is a really common filter when it comes to drone. So technically speaking, complementary filter you can definitely use, but it is not as fast. It's really costly on memory and on space and computation. So in drone industry, in drone hobbies, the firmware we use, so that is the firmware for our flight controller, they implement something called Kalman filter and not complementary filter. Maybe some previous firmwares they have complementary filter, but nowadays I've seen everyone using Kalman filters. And why? Because I've already told you the advantages of Kalman filter over complementary filter. So let's talk about that. So Kalman filter can be used in a dynamic system with uncertain data to help make an educated guess about what the system is going to do next. So this is a very powerful concept of Kalman filter. It will give you a very good estimation of what your system will be going to do next based on the current values and this uncertain data set which you will provide to the Kalman filter, that it will use and do some computation and give you a very good guess. So it's not absolute, it will give you the estimation. It's ideal for system that is continuously changing, and for FPV drones, we are flying it very fast from the gates and doing all kind of maneuvers. So it's really ideal for these kinds of situation. It does not keep history for previous state. As I already mentioned in the complementary filter, it's a need previous value to integrate over time, but nothing of that sort in Kalman. And that is why it's very light on memory and very light on CPU for faster execution. So and again, it's used for optimal state estimation. So it is used to estimate the state of a system and what it will going to do next based on the value which you are providing it. So very powerful concept, and everywhere where you need to use sensor fused values, Kalman filter is a go-to filter. I have seen everywhere. If you want have more than one sensor and you need to get some useful information, Kalman filter is the one thing which everyone uses for sensor fusion. So that was about Kalman filter. And if some of you are really interested to implement that, again, there are libraries available out there. You can use that with your microcontroller, and you can definitely implement Kalman filter. So that was about sensor fusion. Now let's talk about control systems. Alright, so talking about control systems, so we managed to get clean sensor fused values from IMU, but what about the compensation for external forces acting on drones such as wind? So a really great question, and it's simple. So if you are getting clean values from accelerometer, okay, that is sorted. But now what happens when you're flying the drone and some external forces are acting on it? Let's say some wind gust came and your drone gets drifted away. So how do you fight that? So these kinds of things are very important, and that is the reason we actually need flight controller for to exactly do what a drone operator wants it to do, to actually do as it commanded, and to cancel out the effect of external forces, to compensate it, and to give us the entire result that we are asking for it to do. And that is a function of flight control. And again, wind is just one external example that you would need to compensate if you want a stable flight. But what about some internal factors? Let's say you are building a quadcopter, you are using 4 motors, exactly same motor, but since it's mechanical, it cannot be exactly same. Maybe some motor has more RPM than other. I'm not saying it would be have drastically more RPM, but let's say 100 RPMs more because of let's say the manufacturing defects, or it is a bit smoother. So these kinds of things are very common when you are doing some electromechanical system, some manufacturing processes defects and some other things. So because of that, you just cannot achieve the exact system which you have designed or which you have simulated. So that is why you need control system, and in this case flight controller. And you just cannot plug 4 motors and just give them power and you fly the drone, because the external forces and the internal mismatch of the components will not allow you to have a stable flight. And to have a stable flight, you need to compensate for all these factors. So let's take a very good example in the next slide. So let's say this is your drone, and you have given the command to your drone to rotate right in roll axis 2 degrees. So this is your drone, perfectly level, perfectly stable with respect to the ground, and the drone operator has given the command to roll right 2 degrees. You can do that with your remote. Receiver receives the command and passes it to the flight controller that the drone operator wants to rotate the drone in the roll axis 2 degree right. So this will go to the flight controller, and flight controller, what it will do, it will do some calculation that okay, my current angle is 0 degrees. User wants to have a roll right 2 degrees. I need to speed up the left motors, I need to speed down the right motors. How much I need to speed? I need to speed, let's say, X amount. But after changing the RPM, the roll you get is 5 degree right. So why that happens? You wanted the flight controller to give roll you 2 degree right, but you actually get 5 degree right. That is not what you want. That is not a pleasurable flight experience. So why that happens? And maybe because of external wind. You wanted 2 degree, the wind is blowing in the same direction, the overall angle you get 5 degrees, and this is not a pleasurable flight experience. That's not what you want. You want to counteract this, you want to solve this. And so the current value of your drone roll is read by the IMU, and the IMU read it. It says that this is the current value, and the flight controller see that okay, this is an error, this is not right. User wanted me to do roll right 2 degree, but this is 5 degrees, so I need to compensate that. I need to compensate for the wind. So it will generate a command to do -3 roll right. And of course, with that command and with the next user command, it will combine, and it will come back to the flight controller, and this loop will continue to operate. And this is called the feedback loop, the feedback control system mechanism. And if some of you have read it if you're from engineering background, you might have read these kinds of things. So this is a very common control system with the feedback. And the IMU is doing the feedback loop here. So the function of the IMU is to read the current attitude of the drone, to read the current roll, pitch, and yaw, and to keep sending it to the flight controller back. And the flight controller, if it matches it to the what user wanted, and if it's not right, then it will generate a compensate signal to the ESC and again change the RPM, and it keeps on going on. This will never stop. As from the moment you take off to the moment you land, this loop will continue to operate. This feedback loop, this forward path, everything will continue to operate. And that's how exactly the flight controller compensate it by getting a feedback from the IMU. So IMU gives you the current sensor readings, and the flight controller, it matches it to the what user want. And based on that, if there is any error, flight controller wants to do some compensation, and to mitigate the error, it generates a new signal. So that is how the entire drone works internally. And if you talk about something in technical, so in technical language, the value which we want our drone to be, it's called a set point. And the set point is nothing but the desired value, what value we want. So we set a point for the flight controller, and we want the flight controller to achieve that point, and our drone should be at that point. And the actual value which we read after the command has been executed to change the RPM to the ESCs, and we measure it again using IMU. It's called measured value. The value which we have get after the loop is complete. The execution is complete, and ultimately, if the flight controller, what it will do, it will compare the measure value with the set point, the value which it actually gets after executing the command, minus the value the user wanted, the set point. So it will get the error signal. So error signal is nothing but a set point minus measured value, and based off that as error signal and the next value, it will continue to work. So this is the entire block diagram, entire architecture, how the control system in a drone works. So if you actually try to take a bigger look, it's not actually a new concept. In fact, it's everywhere, and we are experiencing it in our day-to-day routine. So let's take an example of this thermostat. So thermostat is a device which controls your central heating and central cooling system in your houses. It's more common in Western countries compared to, let's say, something like in India, but it's the same concept as everything works in terms of control system. So let's take an example that we want your your room to be at 74 degree Fahrenheit. So let's say you have set in the thermostat that I want 74 degree Fahrenheit. The thermostat will have a sensor, a temperature sensor inside it, and currently it measured that it's 80 degree Fahrenheit. So what it needs to do, it needs to bring the temperature down, and to actually do it, it will turn up the AC and it will turn down the central heating system, HVAC. So that is one simple example. Inside this entire control system, the thermostat, it's nothing but same compensation is happening. It will measure the value again and again, and it will keep controlling the AC and the HVAC and see if the set point has been achieved. If not, it will keep doing that until the set point is achieved. Once the set point is achieved, it may try to maintain it. So there might be a chances that the value goes even lower than 74, and it will then bring the heating system up, or maybe bring the cooling system down. So these kinds of things will continue be happening until the system is operating. So that's why I said from the moment you take off to the moment you land, the control system is activated the entire time in the drone. So let's talk about algorithms and controllers. So the entire idea for telling you this compensation of external forces and internal defects by the flight controller, the entire idea of the control system is to minimize the error. That is to have the measured value as close as to the set point value, to give the user best experience, to give the drone exact control as user has demanded, and just compensate if there is any error caused by something like wind or some internal defects. And to minimize this error, the flight controller implements some different algorithms and controllers, and these are the part of control system, the entire control system, and these are nothing but a set of instructions or programmings which implement some mathematical formulas and algorithms. So there are a lot of different control system algorithm that you can use when it comes to having a closed loop feedback system with motive to minimize the error. And these are let's say a fuzzy logic. So fuzzy logic is also a type of control system. All these are nothing but these are algorithms which you implement in your firmware using programming and using some mathematical equations. So fuzzy logic is again a type of control system. There is also a simplest control system like bang bang control system. So what if we have to compare it with the thermostat example? So a bang bang control system, what it will do, it will check if the room temperature has reached a certain point. If yes, it will close down the AC or the HVAC system based on that. So it's very simple to implement. So we'll not talk about fuzzy logic and bang bang, but what we'll talk about is proportional. So proportional, integral, and derivative to be precise. So these three are different controllers: proportional, integral, and derivative, but these three together are being used in drone control system algorithms, and it's called PID. So the thing is that drone is relatively a very advanced system when it comes to minimizing the error, and it does have some present error, and it also has some past error which are getting integrated over time, as we discuss in sensor fusion. And as we discussed in Kalman filter, the Kalman filter is capable of estimating the next value. So we also have some estimations of future, and similarly we can also estimate some error in the future, and that is where derivative comes into picture. So proportional helps to deal with the present error. If a user wants this degree in this axis at present, and if that's not there, the proportional will eradicate it. If there are some error in the system because the past values are getting there, the integral will deal with that. And if we estimate that based on the current rate of change there would be some future error, then the derivative takes into that. So we can use them together, like pi, proportional integral, by totally neglecting that d. But we can, the most common implementation is PID, where we'll use every controller from PID types. So this is the equation of PID. Don't get frightened, it's very simple. So I just want you to focus on this E of t. This is the error signal. So if I go back to a couple of slides, and we talked about the error signals. So error signal is nothing but your difference between the set point what user want and the current value. So in this case, the minus 3 degree is the error which flight controller used to compensate. So I wanted to focus on the error signal only. So what the PID equation is doing, the P part is multiplying the error with a constant k of p. So k of p is a constant, it's not a variable, it's a constant, like 1, 2, 3, 0.3, 10, 11, 11.4, something like that. So it's taking the error signal and it's multiplying it with a constant. So that becomes your p part of your PID, your proportional control system. What I is doing, it is integrating the error over time and multiplying it to a k of I constant. So we have a constant k of p and we have a constant of k of I. Similarly, what derivative is doing, as a name says, that it's derivating the error over time with k of d. So this looks very intimidating, but when we actually understand it, is nothing but we take the error signal, we multiply it with k of p, we integrate it with k of I, and we derive it with k of d. And what we get is a sum of the value which the flight controller is actually generating to compensate the error. So that is the entire concept. You just need to find the error signal, the value of the error. You multiply with k of p, you multiply with the integral of k of I, and you derive it and multiply with k of d, and you get the actual signal and you send it back. So this is the control system which we uses in drone. It's called PID, proportional integral derivative. The motive is simple: to reduce the error as much as possible and to bring the current value, the measured value, as close as to what user requested, the set point, what user has set the point for us. So okay, so this also might be intimidating but might not, but when we come to actually realizing it, there is a lot of maths involved, and you should know how to do integration in coding, how to do derivation in coding. But more than that, there could be one question, that what is the value of k of p, what is the value of k of I, what is the value of kd, and how do we calculate that? So that is the entire concept behind PID tuning. What is a PID tuning? So finding this KP, KI and KD for your system is called PID tuning. Finding these gains. And one more thing I would like to mention here, that this PID is different for each axis. For example, this PID may be for roll axis, but you will need two more for yaw and pitch axis. So you will have PID for roll, PID for pitch, and PID for yaw. And similarly, you will have KP, KI and KD for each axis. So KP for pitch will be different than KP for yaw. So things like that. So what is a PID tuning? Again, coming back to it, it's finding the value of these constants, KP, KI and KD. So as I mentioned, these are constants, and what could be this value? This value could be anything. So how do we find this value? We need to find this value which is fit for our system. So generally there are different ways to find this value. If you talk about drone, what people used to do, every firmware comes with some default value of kpk and kd for each axis. So if you are using Betaflight, which I'm using, it already pre-programmed into the firmware with some good to use, good to start values. But that is not for every system, because every system is different. Everyone is using different motors, everyone is using different propellers. Maybe you are running same firmware in a bigger drone, and same firmware is being by you someone for smaller drone. Maybe someone has hexacopter, you has octacopter, or you have quadcopter. So you need to definitely do PID tuning. Without PID tuning, you cannot have greater results. So you will having your error multiply with a constant, which is not good for a system. That is not good. So ultimately, when you build the drone, when you flash the firmware, the last part you need to do is to fly the drone and see if these values are good. If not, then you need to change it. So finding the right value for this constant, that is called PID tuning. And if you talk about generally in drone industry, in drone hobby, what people do, they fly the drone and they know what to observe when the drone is flying, and based on that observation they comes and make changes. For example, if you have given some command and your drone is taking longer to process that command and there is some delay in the process, then you need to increase the kp or the proportional, because the multiplication constant, if you increase that, it will give you the more results, the more multiplied results. So things like that. But that is something that does not comes in one class. So this is something that you need to learn, and you need to see by reading forums and how people, so because everyone is having different method of PID tuning. So let me discuss some methods of PID tuning. So number one is tuning using simulation. So what you can do is you can design a drone in simulation. You can design a drone in software, and based on your drone parameters, let's say you fix that this is 2200 kV motor, this is this battery. Based on that, you can get some values for kpk and kd. So you let the computer decide it. But real life is very different, and the best part is your tuning by observation. So as I mentioned, a small example, if your drone is a bit laggy, it has some a lag, so when you give a command and it takes a significant more amount to execute, then you need to increase the kp and so on. So you tune by observation. One thing that is also was very common a couple of years back, when new people are coming into this hobby and they were not from technical background, they do not understand kp, ki and kd and PID tuning. So some firmware has a feature called auto tuning. So what is auto tuning is, you take off your drone, you bring it to certain height, and then you switch the auto tune on, and it will do some motion in all the three axes, and based on that motion it will set the value of kp, k and kd for you by auto tuning. But the disadvantage is that auto tuning is not very accurate. It's a good ballpark number, but it's not very accurate. How it do is because if your values of kp, k and kd is very high, then your system will have vibration. So it will keep on increasing the value until some vibrations come into the system, and as soon as the vibration come, it stops and dial down the value. So even while observing, we do this. We keep on increasing the kp until we see some vibration, and as soon as the vibration comes, we dial down the value. So these are the methods of PID tuning, and I would highly recommend, if you're building the drone and you want to PID tune, just find what is the best method people are using these days, and if there are some tools for that. Another method that I have not mentioned here is something called black box logging, and I didn't mention it because not every flight controller has option for black box logging. So what is a black box logging? It's basically logging your flight data into an SD card and then analyzing it using a software. So you log the data that at what particular instant, what command you gave from the transmitter and how your drone reacted. So based on that, you can bring that into the computer and you can see that, okay, I have given my drone command and it take 2 milliseconds to react. So it's a high delay, and you increase the KPs, things like that. And you also observe that, okay, now my drone is having vibration on your axis, so you can dial down. So this is another method which I used to do like a few years back. But I would highly recommend you read more about it, especially the tuning by observation and how to tune that. So it's something which is very important, because the default values are not going to help for longer run. All right, so let's talk about the flight controller firmware. So this was a relatively very advanced class where we discuss about digital signal processor. We discuss about implementing complementary filter and what is notch filter. We also discuss about control system and algorithms, proportional, integral, and derivative. The question is, if I want to design a flight controller, do I need to program everything into that? The answer is yes, you have to. If you want to have a stable flight, then you need all that. You need signal processing, you need to understand how IMU is communicating with the CPU. You need to understand if they're communicating in I2C. You need to know how I2C works and how to get data from I2C bus. The protocol implementation, writing drivers. You also need to understand that once you get the data, that you need to do some filtering to get a good data. You need to apply some notch filter. Then you also need to do sensor fusion by applying Kalman filter on complementary filter. Then finally, you need to implement the entire closed loop feedback system that I showed, and you need to have a control system PID or something like that in place. So is that really difficult? The answer is yes. It's not something for complete beginners. If you want to do everything, you need to have good knowledge of electrical systems, electronics, control system, and DSPs. So another question could be, so I don't know that, so I cannot fly the drone. The answer is no. Because there are some open source projects with good people who already have this knowledge and make these programs available free for you. You can just use that. You can download the firmware. You can flash your flight controller with this firmware. You can tune on the graphical user interface, and you are good to go. So yes, you do not need to code everything from your own knowledge. So I want to show you one such example. So let me show you the source code for one of the project that I use. So I use Betaflight. Betaflight is an open source project, and open source project means that the source code is freely available for everyone to see and modify and see what's happening. So it's github.com/betaflight where the source code is located. So you can see github.com/betaflight is where the entire source code is located, and it supports a lot of flight control, and you can see it's under active development. It has 215 issues and 23 pull requests, and latest release came back 4 days ago, that is 4.2.3. So yes, it has a multicolor RGB feature, D-Shot, as you mentioned in the EAC chapter. It supports D-Shot. I was just saying about black box flight recorder. It supports S-Bus and all kinds of receiver connection. So yes, let's see how these kinds of things are implemented in source code, just for the fun. So if you go into the source directory, and if you go into, let's say, utils, and this is where the not utils, the main, where the fun part is. So you can see that there is a source for everything, and I am interested into FC, the flight controller, or not. I'm interested in the flight. What happens when we are taking a flight? So you can see IMU.c is here, which is having the source code for inertial measurement unit. There are some helper libraries like gyro analyze or mixer.h, maybe something for sensor fusion, and I want to see, yeah, there we are. We have PID.c and PID.h library. So let's see what's happening in IMU. So if I open IMU.c, this is the source code for reading value with the IMU, and you can see a lot of libraries are involved here, and you will see a lot of maths happening. Attitude, reset, gyro limit. So this is just a small example where exactly it's very big, but it's a small example compared to the entire project. Now let's see about the PID. So how the PID is implemented. So this is the implementation of PID in Betaflight. I might be able to show you if there are some values for KPK and KD. So yes, here you can see that PID role 4285. These are, I believe, some values which you get if you reset the PID profiles. So in Betaflight you have 4 different profiles for PID. I mean, you can change different profiles based on your drones, and you can see what value is good for you. So these are the 4 values for 4 different profiles for roll. These are for pitch, and these are for yaw, and things like that. So I'll want to show you the Betaflight configurator. That is, if you are willing to just use this flight controller firmware without developing your own, how that would look. So for that, I'll open Betaflight. Okay, so this is the Betaflight configurator, and you can see here is a firmware flasher. So you can go here and you can select your flight controller, and it will fetch the latest firmware and flash it with that. So you can see these are all the flight controller it supports, and the list is really big and a lot of flight controllers are there. So you can choose your flight controller, you can choose which build you want to flash, and then you can flash it. Once you flash it, I will not flash because I already have. So I've connected my drone, my flight controller, using a USB cable to my computer. So once you flash it, you can connect it and you can go inside the configurator. So this is how the configurator looks. So I wanted to also, so there are a lot of videos you can find about PID tuning in Betaflight, and what I want to show you is how that looks. So okay, as that's what I wanted to show you. So this is a PID tuning page on Betaflight, and so you can see here it says proportional roll 50, proportional pitch 80, proportional yaw 90. So these are the value of KP for each axis, and similarly for I and similarly for D. So this is how you can change it, and this is how you can tune it. So if you think that your KP is less for pitch, you can come back after the flight, you can increase it, you can save it, and you're good to go. So that is about firmwares and how you can use an open source firmware and flash your flight controller with it, and tune the parameter which you want to do. So also that was all for today's class. Thank you very much for joining today, and everyone who signed up for this course. It was really fun experience to interact with you all, especially during the office hours. We started with the drone frame selection and propeller selection. Then we moved to motors and ESC, to transmitters and receivers. We talked about protocols. We talked about communication link, frequency, channels. And today we talked about digital signal processing and control system, which are a really important concept and used everywhere in control system industry. So it was really fun for me to teach, and I really enjoyed being the instructor for this course and interacting with you all. So I'll see you tomorrow for the office hours for this class. So if you have any doubt, please show up. And thank you very much for joining, and I'll see you sometime later. Bye.